Hello and welcome back to Precalculus, section 4.8 on word problems with trigonometry. So, as always, mathematical concepts can be applied to what you would call a real world and situations. So, we can use trig to compute a lot of cool stuff. We can start by solving the basic triangle. Basic right triangle, and then we can go from there. Now, what does it mean to solve the basic right triangle? Well, that means to calculate the values for that triangle. So, if I have, let's say, a triangle of any kind, literally can look any way you want, and you put angle in that triangle. Immediately what you have is the opposite hypotenuse on the longest side and adjacent on the side that is touching the angle. So that's the automatic response. Then you can also quickly assign A, B, C, D for the sides. And you can also assign A, B, C, D, I mean A, B, C, D, A, B, C, triangle, so three. So A, B, C for sides and A, B, C for angles. So if you call this, let's say, A, then across the street, that should be A. And you call this a B, then across the street, that should be B. Call the C across the street, that should be a C. And then you also have A squared plus B squared equals to C squared, which is known as Pythagorean Theorem. But you also have 6 trigonometric functions that you can write for this triangle, which would connect lengths of sides with the which will connect lengths of sides with the angle. So you can have sine of angle A, which is our theta, and sine of A would be opposite, which is A, divided by hypotenuse, which is C. You can have a cosine of A, and a cosine of A is adjacent, which is B, divided by C. And the tangent of A is going to be opposite A over adjacent B. We don't really use the other three to set up triangles and do word problems. I mean, we can, but really there is no need. So we can write them, but no one ever uses them. They are going to be insanely useful in calculus later on, and derivatives and all that kind of stuff. So we will have to know secants and cosecants and everything else. But for the word problems, for the purposes of this one section, we really don't need secant, cosecant, and cotangent. Like these three are enough plus Pythagorean theorem. And that's really cool. Now, another formula that tends to be very useful for word problems here and there is the formula which computes, the sum of the angles of a triangle on a flat surface is 180 degrees. So A plus B plus C equals 180 degrees, but that's only when the triangle is on the flat surface. That doesn't hold when the triangle is on the curved surface. Like if you draw the triangle, or let's say on top of the ball, like you take a basketball, let's say, and you take a thick Sharpie and you draw a triangle on top of the ball, the sum of the angles is going to be bigger than 180 degrees. And if you draw the triangle, if you have a round cereal ball, like a round, like a half a ball cereal ball, and you take a Sharpie and you draw a triangle inside on one of the sides, right? You know how the ball, when you look at the ball like this, the cereal bowl. So you go on the inside and you draw the triangle here. the sum of all angles will be less than 180. But when you have the flat surface, the sum of the angles is exactly 180. So these are the formulas that you need. And now, what you can do is you can go and compute a lot of stuff. See, I can give you a right triangle and only two things, and you can compute everything about that triangle. So let's say you have the triangle given like this, and then again, remember the rule is across the street. Across the street, across the street, across the street. Good. So the right angle is obviously where C is. So now let's pick problem number, it doesn't matter, 6, whatever. They tell you that angle B is 23.8 degrees, and then tell you that the side B is 40.5. Inches, centimeters, meters, miles, I don't care. Some unit of length. So how do you solve this triangle? Well, you are given this angle and this side. If this is, and why do I circle this angle? Because I want to know immediately where to put my opposite adjacent hypotenuse. That depends on angle, because I know this one is always going to be hypotenuse because that's the longest side across the street from the right angle. It's always the longest side. But the two other legs, A and B, like each one of them could be opposite, each one of them could be adjacent. It depends where the angle is. So B, being the angle, makes this an opposite and then makes this adjacent here, because adjacent leg is the one that's touching the angle, and the opposite leg, right? The shorter sides of the triangle are called legs, and the long sides called hypotenuse. So one of the legs is always going to be opposite, and the other one of the legs is always going to be adjacent. So now, when you do this analysis here, B is the angle, so across the street is the leg that does not is not adjacent to it, right? It doesn't touch it, which means that's the opposite side. And as soon as I have that, I can just go and compute literally everything. Because if I write my, let's say, tangent. Why did I pick tangent? Whatever. You want sine, let's write sine. But I'm going to write tangent, let's say. Tangent of B is equal to opposite over adjacent. And I have values for this. And you can see that I can calculate the length of side A when I solve this equation. Tangent, now make sure in mode you switch to degrees in your calculator. That's important. So now that you are in degrees, you push tangent, and then you type 23.8. That is going to give you 0.441. 40.5 over A. And now when you solve this, right, A is equal to 40.5 over 0.441. So 40.5 divided by 0.441, and I get 91.8. Why am I not putting 16 decimals? Because this side, B, was given as 1 decimal. So let A be a side with also one decimal. Okay, there we go. So now I have A, I have B. Well, we can use Pythagorean theorem to figure out C. Okay, let's use Pythagorean theorem. C as the longest side is the square root of A squared plus B squared. So that's 91.8 squared plus 40.5 squared. And 91.8 squared plus 40.5 squared is 10,067.5. We square root that answer. And we get 100.3. 100.3. So I have A, I have B, I have C. Now I only have one angle. I need one more angle. And this is where, well, actually, no, I don't need any more angles, sorry, because I have that angle C is 90 degrees. What am I talking about? Angle C is 90 degrees, so we can just use the sum of all angles is 180, and you can find A. So, since C is equal to 90 degrees, make sure this is a lowercase c and this is the uppercase c, right? Since 90 degrees and angle B is 23.8 degrees, angle A is 180 minus 90 minus 23.8 degrees, which works out to be 66.2, right? Degrees. And now I have my angle C and the angle A, and I have all six, right? We need to have all six of them. You have 4 over here and 2 on top that are given. And we say this triangle is solved, meaning I know all 3 lengths of the side and all 3 angle measurements. I know all of them. And that's why I claim that this triangle is solved. Done. Any questions, concerns about this? Okay, so there are some subtleties, obviously, that you will discover as you go, and then we are going to discuss them, obviously, the next class if you need to. Let's take a look at. So there is this other, like problem 12 gives you 2 sides, and you already know that there is an angle, right? C that it's 90 degrees. You always have that 90 degrees given, basically. So for problem 12, you have B is equal to 4 and C is equal to 9. You can immediately get your A without much thinking, right? Which is 81 minus 16. Yes. So that's what? Square root of 65. And square root of 65 is very close to 8. It's not 8, but it's like square root of 64 is 8. So this is like 8.0 something. So A is a square root of 65. 8.06, as I said. So now you have 3 sides, but you also have that the capital C, right, which is the angle, is 90. So you just need to find one angle out of capital A, capital B, one of them, and the other one you can just subtract from 180. So now we can draw the triangle. Again, draw any way you want. Just make sure that capital C and lowercase c are opposite, capital A and lowercase a are opposite, capital B, lowercase b are opposite. And let's say you want to write sine of A. So you want A to be the angle you find. Okay, well, if A is the angle you find and you want sine, that has to be opposite over hypotenuse. So opposite over hypotenuse, looking at the triangle. Now you already have A and C, right? It's 8.06 and C is 9. So sine of A is, leave some space here, divide 8.06 by 9. And you get 0.895, 896. Now, why did I leave some space? To solve this equation for A, you need to hit both sides by inverse sine. That's why we learned our inverse sines last time, so that can free up our A, and then you just need to find the inverse sine of the previous answer, and that's 63.6 degrees. See, it's very quick, right? We used the Pythagorean theorem to find the third side, and then we used literally any trig function of any angle to find either A or B. We found A, so B is going to be 180 degrees minus 90 degrees minus 63.6 degrees, and that's going to be 26.4, as I write 16. 26.4 degrees for angle B. And then I have my 6. 1, 2, 3, 4, 5, 6. There they are, all 6 calculations. We have 3 sides and 3 angles. Now, obviously, C equals 90 is always given because every triangle that we deal with right now is a right triangle. We are going to do this for general triangles, guys, but in chapter 6, right? We need to get there first to chapter 5. But we are going to learn 2 sections in chapter 6 that deal with the triangles that don't have the right angle. And it's still possible to use all of this stuff, which is amazing. So these would be the introductory problems. They're not really word problems. They're more like concept problems, because we didn't do any application here. It was just solve the triangle, get the values, and move on, right? Now, let's take a look at the word problems that we get to see for trig functions, right? And we already talked about calculating heights and lengths. So the trig is really good, and you can actually use it to calculate the height of the house you're in, or the tree, or something, as long as it throws the shadow. So imagine, right, that you have some kind of a, let's say a flagpole, right? There's a flag there. There we go. And you want to figure out the height of it. And there is a shadow on the ground. And that last sun ray, right, hits right there. You know there is a 90 degrees over here. And you can take the tape measure and measure the length of the shadow in feet. So, because that's on the ground, right? So you just take the tape measure, you stretch it, right? and figure out the length. So let's say you measured the length and it's, I don't know, 36 feet on the ground. So now this angle here you can measure with a protractor, because if you put your face on the ground and look up at the top of the pole, right, and you bend a piece of the wire or something that aims directly to the top of the pole, by putting up a protractor on the side. Protractor, if you've never seen one and you don't know what that is, it's a plastic device that measures angles. Looks something like this, and it has divisions, right, for all angles along. It's transparent, so you can see through, and goes on this side as well. And when you take that the way and you put it right here against that wire, the wire will just have a dial, would act like a dial, and will tell you, oh, okay, that's right on a scale from 0 to 90 degrees. That's how many degrees you have. So let's say that you measure that angle there, call it angle A, and let's say that that angle A was, I don't know, 31.4 degrees, because you really did good job measuring. So how tall is the flagpole? Well, when you put your angle there, this becomes the opposite side, and you are interested in it because that's the height. And you also have this side because that's what you were able to measure, so adjacent. And in this case, we don't care about the hypotenuse because we don't care how long is the sun ray over here. We don't care about that. So we will set up a tangent. Tangent of 31.4 degrees is equal to opposite, which is what you don't know, divided by 36 feet, which is what you measured as a shadow. So when you multiply both sides by 36, age is equal to 36 tangent 31.4 degrees. Now I made up these numbers, so this could easily be terrible, but I mean in terms of the answer. So 36 times the tangent of 31.4, and I got, well, 22 feet. 21.97, that's 22 feet. Not that bad. 22 feet. It was 21.97 feet, but do you actually use that language? Right? You don't. When you see something in the store for $3.99, you know it's $4. Right? It's not $3, it's $4. So you round it up. So 22 feet is the height of the flagpole. Plus the question is how, well do you measure this and so on. Now there are other problems that you can solve, and they all involve the triangle, clearly, right? What I see here is a little kid that's playing with a kite, and when you drop this vertical here, you can know the length of the rope. because you know that you bought the rope that was 65 feet. Now, one thing that I don't like about this problem is that somehow this kid knows that there is a 30 feet height. That's not a good problem, because kid is not going to know that. Much better version of this problem is to say that kid knows that this is, let's say, 40 feet over here instead of 30. So I'm going to delete this 30 feet and I'm going to pose the problem by this, because guys, this would be the shadow of the rope over here. And that's information that you can measure as a kid with a simple measuring tape. You can't measure that height of 30 feet. Like, first of all, kid is not even, like, what, 5 feet at most? So it's not going to be, a kid is not going to be measuring the height 6 times, right? His or her height precisely in the air. But once the kite is flying, you can tie it to a stake or something in the ground, and then you can measure the length of the shadow. That's much more appropriate problem to have. And now the kid can figure out the height. Now the kid can also figure out at which angle the kite is flying, which is the question in the problem. So, I like these situations, right, to think about them for the scenario that you could actually, do tomorrow if you have measuring tape and a kite. And if there's wind, right? So now, if I call that my adjacent, right, and this is the opposite, I can figure out that the opposite squared is going to be 65 squared minus 40 squared. And I can find the length of the opposite side. You can call them A, B, C if you want to, but whatever. So let's take a look. 65 squared minus 40 squared is equal to 2,625, and then the square root of that answer gives me that this kite is 51.2 feet up in the sky. That's how high it is. Okay, fine. So that's the height. And it's really cool that we can calculate that. And then the angle. Well, now that you have all of these dimensions, literally pick any of the three trig functions, because you have all of the sides. And then you will have to use the inverse, right, to solve the equation. But let's use the given values, right, these two. So you're using adjacent and hypotenuse. Can anyone tell me which trig function is adjacent and hypotenuse?
Cosine.
Beautiful. Cosine. So cosine of the unknown angle, call it theta, you can put capital A, you can put anything, is going to be adjacent over hypotenuse. Yay! So after dividing 40 by 65, we are going to have, now leave the space, remember, leave the space, leave some space, 0.615. And now you hit both sides with the inverse cosine to kill the cosine here, and the angle at which kite is flying, push your inverse cosine in the calculator, bring the previous answer in, at 52 degrees. It's 52.02, yeah, right. So it's flying at 52 degrees. Just by knowing how long is the rope for the kite, which says on the packaging, I hope, and if you just unwind everything, and the only thing that you have to do is to measure the length of the shadow on the ground. And you will be able to calculate everything. Calculate the height of the kite, calculate the angle at which it flies. And that is another type of a problem. Now, I just want to see if they have anything else that it's quick, because this one with the similar triangles is not quick. Bearings problems are not quick. Simple harmonic motion, also not quick, so we'll have to deal with that next time, since all we have is 5 minutes or 4 minutes. Let's take a look if we can find something in our homework. Okay, problem 46 with a police helicopter and a stolen car. I will never forget this. I had the airplane because right when I moved in to US, I had to take exams for math and so on to place into whatever class I'm supposed to go. And obviously, because I didn't speak English very well, it was a challenge for me to translate these problems. And I had the same problem that you see now is what I had, but it was an airplane that was dropping a crate of some kind. And when they said the angle of depression, I had no clue what that meant. So it always stayed in my head. But anyway, let's put the helicopter here. Look at that. Perfect. Oh, can't do without that. So there is the police helicopter. Maybe we can do that shield. Looks like a carrot, but that's okay. So that's the police helicopter flying over Mother Earth at 800 feet. Now you have that information because it's on your instrument in front of you. And there is a stolen car. That's a terrible car. The problem is that I draw these tires too close, and then it's just looks like a Batmobile. Or now I made it worse. Whatever. There's a stolen car fleeing, and the question is how far this car is, the distance, right, from the helicopter. And there is one more piece of information, and that is that what I mentioned, angle of depression. Now, angle of depression is the angle that this one at 72 degrees. So when you are flying and you look forward, right, that's the line of sight, and then you look down, it's the angle of depression. Looking up is the angle of incline. So at the angle of depression of 72 degrees. Now it's probably a way to measure that. So how far is the car from the helicopter? Well, we know that this is 90 degrees. We know that this is hypotenuse. And now, is there any angle that we can quickly compute? Anyone? Because the angle that it's given is outside of the triangle. So it's kind of useless to me. I need an angle inside the triangle so I can compute stuff. Can anyone spot the angle that it's easy to compute? Yes, no, whatever?
The on top, right? Because that's like a 90 degree, so it'll be 90 minus 72.
Excellent. That's one of them. So that's going to be 18 degrees, right? Because they have to add up to a 90-degree angle there. Excellent. There is also a theorem in mathematics that when you take two parallel lines and you intersect them with the line like this angle, this angle, this angle, and this angle all have the same measurement, which immediately means that this angle here is 72, which you can actually, now that you know that this one is 18 and you know this is 90, then this one, right, 180 would bring that to 72 anyway. So either way, you either define the number on the bottom as 72 using the theorem, or you find that one on the top because they add to 90, right? The complementary angles. Okay. So once we dealt with that, then I know if you want to use that angle as 18, that this is your opposite and this is your adjacent. So there's your tangent of 18 is equal to opposite over adjacent. So the distance is 800 tangent 18 degrees. You have to put the little circle for degrees because without it, it's a radians. So it's a requirement. All right, 800 tangent 18, and we are done. 259.9 feet. Distance is 260 feet. There you go. Boom. So easy when you know trig. Next class, we are going to deal with another two types of things here. We have to deal with problems that would have you compare two right triangles as similar triangles. And we need to talk a little bit about simple harmonic motion and that kind of stuff, which obviously helps you a lot with physics later on. Any questions, concerns before we end?
No.
All right. I will see you all later.